So let's look at this case here. Here is a carbon-14 isotope, meaning carbon usually has 6 protons and 6 neutrons, but this particular carbon, which is a rare one, and also used for dating, um, meaning figuring out how old something is, how old a life organism form is, of bones that you find buried for years or whatever. You use carbon-14 dating, and we'll talk about that maybe later as well. But here's a carbon-14 isotope, and it has 8 neutrons and 6 protons. These neutrons, the weak force causes one of these neutrons decides he wants to become a proton, and so obviously can't just create a go from neutral to positive. So it has to also not just become into a proton, but at the same time release an electron, so that it releases it right there. And we can see that the carbon-14 changes from 6 protons to 7 protons. Remember, the number of protons is the atomic number that decides what element that atom is. And so in this case, a carbon-14 has now changed to nitrogen-14. So it's an entirely different element now. It's going to have nitrogen behavior versus carbon behavior. And and so thereon it goes. And this is what we call a beta minus decay, and because a negative particle is being given up. And then in this case, we see carbon-14, and in this case, we have a proton that decides he wants to become a neutron. And so it goes from 6 protons to 5 protons, and then one more additional neutron now here. And so the positive particle can't just create a neutron, it has to leave out a positive particle. So here's a positron. That's the antiparticle of an electron. And these two antiparticles, they meet each other, they annihilate each other, and it becomes into all energy. The particles just disappear. Kind of cool. So the electromagnetic force, of course, you guys already know that one. It's the one we see around us in terms of a magnetic thing, and then the particles, you see this as static electricity and felt it that way, as well with the attraction of the balloon and things like that. Now we come to the strong nuclear force. I'm sure you guys have always asked this question. Hey, look, if the nucleus is made up of a whole bunch of positive and neutral particles, and positive particles repel each other, then how is the nucleus held together? Shouldn't it just fly apart? Because it just has a whole bunch of positive particles and some neutrals, but the neutrals don't really count. They don't do anything. So you clump a bunch of positive particles together. They don't want to be together. They want to just spread apart. So why do atoms even exist? Why do we even exist? And that is where the strong nuclear force comes in. It works at really short distances. That means so within the range of an atom, let's say one atom away from an atom, it has a really, really strong force. It'll pull anything that comes near it. But if you're a little bit further away from that, you can barely feel it. Okay, so that's what we call a short range force. It only acts when you're really close to it. So it binds protons and neutrons and holds them together. It's like a glue, and keeps protons from repelling each other. And if it is disrupted, it releases a whole bunch of energy. So here we have our four forces together: the strong, electromagnetic, weak, and gravity, and an idea of their strengths. And if you look from here, 10 to the power of 2 to 10 to the power of negative 43, that's a magnitude of 10 to the 45. It's a difference between the strong force and the gravity force, and 10 to the 45 is a huge number. Okay, so now we come to this E equals mc squared, and I talked about how the particle and antiparticle would annihilate each other and how particle mass becomes into energy. Well, usually in the case of the radioactive decay as well, we have a change of from the amount of mass to the amount of energy as well. And there is a certain amount of mass that's lost in that process, and that becomes into energy. And that's the energy we see, usually in the form of a kinetic energy. And so here we see that mass is a form of energy equals mc squared. And if you see that a little bit of mass, now this is a huge number, isn't it? C is